Now we talk about convergence of homology spectral sequence. So you can find this on page 34 of McClary's book User's Guide to Spectral Sequence, but there the proof is in cohomology, and here we are going to talk about homology spectral sequence. So again we are working with a graded module A, and differential is D, and degree of D is -1 because we have homology here. So again Z infinity PQ, this is defined as FP AP plus Q intersection kernel of D. So this P plus Q you can say is equal to N. So this is just the definition of Z infinity PQ. Now consider this standard projection map from kernel of D to kernel modulo out the image. So this is the definition of homology of AD. So from here, if you take the projection map here that you modulo out the image, what you will get is the homology. So instead of AP plus Q, you will write HP plus Q. So from here, you have gone here just by quotienting out the image. So now you can see the filtration here is induced by the filtration here. So filtration on homology is induced by filtration of Z infinity PQ, because homology here you can see is a submodule here. You have just quotient out the image. So now we have this map Z infinity PQ to E infinity PQ, and you have the standard definition. The only thing you have to notice is that B infinity PQ, this is a submodule of Z infinity P minus 1 Q plus 1. This is because this consists of image which lies inside here. So this pi here, this projection map, induces this map D infinity. So you first go eta infinity to E infinity, that is this map, you copy right here, and from here you apply D infinity. That means apply this pi to the numerator and apply pi to the denominator. Now this B infinity PQ lies within Z infinity P minus 1 Q plus 1, therefore you can ignore this completely, and you know pi of Z infinity PQ is FP HP plus Q AD, just we copied here, and similarly pi of Z infinity P minus 1 Q plus 1 is just this FP minus 1. So just this filtration right here. Now it is easy to see why this B infinity PQ lies inside here. So this B infinity PQ, you have something which intersections with image of D, but image always lies within kernel of D, and you have kernel of D right here. So you get this. So now notice that our spectral sequence will converge. So it will converge because you have only finitely many non-zero terms. So we are working with a bounded filtration right here, as you can see. So if you take something after this value t, then numerator would be ft, denominator would be ft, because it's just becoming constant, it doesn't change, so you will get a 0. And if you go below s, then you anyway have 0. So if you go below s, deeper into the filtration, you will get 0. You go above t, you will get 0. So you only get finitely many non-zero terms. So finitely many non-zero terms. So now we want to show that this D infinity is actually an isomorphism. So it is clear that this is a projection map, because from here you have a projection map. So you are just taking this projection map to this projection map, because you're not removing anything or adding anything new. So let us see that this is an iso. So this E infinity PQ, this you copy right here, this kernel you copy here, and this Z infinity PQ you copy here. So now we just take this right here, we copy this entire thing right here, and this is right here, the numerator is right here, and the denominator is right here. And you can see the projection maps applying pi, you're just applying pi to it. So this map is injective, you have injective here, you have surjectivity here. So notice that what is 0 here? So 0 here is precisely the denominator, that is 0 is coming from here, and this 0 gets mapped to 0 here. So 0 here is nothing but 0 in the denominator, but this 0 is coming from here, and you can see that this 0 gets mapped to 0, and there is nothing else which is getting mapped to 0. So you can see that this map is also injective other than being surjective. So this D infinity is actually an isomorphism. So this D infinity is an isomorphism. So notice that we had talked about before that on page infinity you can read off the homology groups from the anti-diagonal. So say your anti-diagonal is given to you like this, and say you want to compute say h5 and everything lies in the first coordinate, that is in the first quadrant, then the homology groups will lie on this anti-diagonal. So these are the coordinates where our h5 lie, and then you take the direct sum of these coordinates. The only problem is that sometimes the sums might be jumbled up, or on the page infinity you cannot distinguish between certain groups. You can only see the homology up to direct sum. So you can only see it up to direct sum. So I want to give an example of this so that this becomes more clear that what is the problem we encounter on page infinity. So let us see an example. So consider a double complex like this. So say this diagonal is our C0 and this is say the coordinate 0 0, and this is this map Z3 to Z9. So say this is multiplication by 3. So this is an injective map, and this map is multiplication by 1. So this is actually an isomorphism. So this is 0 0. So this is our C0. If you consider anti-diagonals, C1 is direct sum of Z9 and Z3, and C2 is just C3. Direct sum of zeros doesn't matter. So this is C1, this diagonal is C0, and this diagonal is our C2. So this is how it will look like. So this is our C0, this is our C1, and this is our C2 in terms of total complex. So if you're looking at a total complex, this is how the total complex looks like. So element x here gets mapped to 3x here because this is multiplication by 3. So first coordinate is multiplication by 3, and the second coordinate is just isomorphism, so multiplication by 1. And in terms of spectral sequence, this is how it fits. So we are going to compute it in two different ways. One by using column filtration, and then by row filtration. So let us first focus on the column filtration. So using column filtration, our page 0 will look like this. So you have elements like this. So this map is iso. So you have 0 coming in, 0 going out. So you compute the homology, it's just C9. Since this map is iso, this is injective as well as surjective. So you compute the homology here, you will get 0. Compute the homology here, you will get 0. So the only non-zero item on page 0 is Z9. So this is how page 1 will look like. And now you can see this entry Z9 kind of stabilizes. So there's nothing else to do, and so this will look exactly like page infinity now. So on page infinity you will just have Z9, and this Z9 sits right here on C1. So you get the homology groups as H1 is Z9 and all other homology groups are 0. So H0 is 0, and for H2 and higher they are all 0. So Hi greater or equal to 2 is also 0. Whereas if you use row filtration, this is how your page 0 is going to look like. So for row filtration we are transposing this. So this 0 thing is right here. This row we are putting right here like this. This row we are putting here like this. And this row we are putting here like this. So notice here you have this injective map multiplication by 3. So you put this as injective map multiplication by 3. Start computing homology. You get Z3 here. This is injective, so you get 0 here. This you get Z9 over 3 Z3 will just give you Z3. So the only non-zero entries are Z3 and Z3 right here. So on page 1 we will just have two non-zero entries, Z3 and Z3. So this is how page 1 will look like. So as you know, the Z3s will stabilize. On page 2 you will still have these Z3s, but this arrow is going in here and this 0 is mapping in here, and then you go out to another 0 right here. So basically these threes kind of stabilize. So this page 1 will also look as page infinity. So now we have H1 is Z3 direct sum with Z3, because these two modules just sit where C1 is sitting. So they are still sitting at C1, as you can see. So you still have Z3 plus C3. And H0 is just 0, and H2 is also 0, H3 is also 0, and so on. So here we are getting H1 as Z9. Here we are getting H1 as Z3 plus C3. So this is what we mean that this spectral sequence cannot distinguish between Z9 and Z3 plus Z3. So notice that, you know, Zp square, you can write it as so if you have an abelian group P square, you can write it as Zp square, or you can write it as Zp direct sum with Zp. So we in such a case, in spectral sequences, we cannot distinguish between Z9 and Z3 plus Z3. So this is an important point. So the question still remains that what is the homology of this complex? Is it Z9 or is it Z3 plus direct sum with Z3? So for that, we will have to use the total complex and compute the property from here. So if you actually compute the cosets, we write it them like this: 0 0 0 1 0 2 1 0 1 1 1 2 2 0 2 1 2 2. So if you compute the cosets here, that is, kernel is this entire map. So homology here is kernel is the entire map. So kernel is Z9 direct sum with Z3. So this is the kernel over image. So image is this map. You have direct sum Z3 here, and then you have 3 times Z3 here, 3x and x. So if you compute this, you have to write down all the cosets, and these are the cosets. So if you see the cosets, you know that this is equal to actually Z3 direct sum with Z3. So again, the spectral sequence was unable to distinguish between Z9 and Z3 direct sum with Z3, and this is kind of a phenomenon which is often found.